Hello, my name is Ondřej Lengál, and I will present our paper on regular expression denial of service attacks on non-backtracking matches. This is a joint work with Lenka Turoňová, Lukáš, Holík, Homoliak, and Tomáš Vojnar from Brno University of Technology, and Margus Veanes from Microsoft Research. What is a regular expression denial of service attack? It is a denial of service attack performed by giving a regular expression matcher, that is, for example, in some websites to validate input fields, some very hard text that makes it slow down significantly. For a concrete example, suppose you have a 500 kilobyte file containing some pretty random characters, and you want to check whether there is an A followed by 500 characters before the end of a line. This is a regular expression that we are looking for in the input file. The runtime for this is pretty fast. It is done in 80 milliseconds. Then consider that you have a different file that contains all A's, and you try to find the same regular expression there. Now the runtime is much slower, 1.52 seconds. This is 19 times slower, and in some cases it might be considered to be a ReDoS. Note that this is only a very simple example that could fit on one line on this slide. In practice, the slowdowns can be much higher, as we will see later. ReDoS is not only a theoretical toy, but it is a real-world threat. For example, in 2016, Stack Overflow was taken down for 32 minutes because of a very simple regex and some malicious user submitting a command that contained 20,000 spaces and an A at the end of a line. Moreover, there have been ReDoS vulnerabilities detected in popular frameworks for making websites, such as Express.js, where you could attack the package negotiator by submitting some evil text inside an HTTP header field, or Node.js, where the package URL regex could be attacked by submitting some evil text in the URL. The cause of these ReDOSes is often the use of backtracking matchers, which are matchers that use non-determinism and backtracking to match an input text. These are used, for example, in PHP, JavaScript, Perl, Ruby, or .NET. They are the default matchers there. The common advice of how to deal with ReDoS is to use non-backtracking matchers, sometimes also called linear time matching engines or matchers based on Thompson's algorithm. This has been advocated, for example, in these three papers. There were more papers. This is just some example. And they say that as long as you use this kind of non-backtracking matchers, then nothing bad can happen to you. Well, we show that this is actually not true. And even if you use the non-backtracking matchers, you can still be vulnerable to a ReDoS. Let us now recall how non-backtracking matchers work. The textbook algorithm starts by constructing a non-deterministic finite automaton for a given regex. Then the automaton is determinized into a deterministic finite automaton, which can track all possible runs of the non-deterministic automaton in its macro states. The states here are called macro states because they contain states of the original NFA. After the DFA is constructed, we can then perform a match in linear time. The issue of this approach is that the DFA that would be constructed might often be too big. For example, in some applications in network intrusion detection, the DFA would have billions or even more states. Therefore, in practice, a different algorithm is used. It's the so-called Thompson's algorithm that also starts by constructing a non-deterministic finite automaton, but then the DFA is not constructed a priori, but only on the fly, so that only the useful parts are constructed while the input text is being matched. The constructed parts are being cached, and this often gives you a linear time matching complexity. Tools that use this approach are, for example, grep, RE2 from Google, the matcher in Rust, SRM from Microsoft, or Hyperscan from Intel. Actually, Hyperscan uses a little bit different algorithm that doesn't use the caching. However, we observed that these matches can still run slow. And the reason why they run slow is when there is low cache utilization. Because the cache is often reset, then the linear time complexity is not achieved. The question is whether we can address this and have an approach that can systematically generate regular expression denial of service attacks on these non-backtracking matchers. And the answer is yes, we actually can. And we do this by exploiting counting in regular expressions. Counting is a feature of regular expressions, sometimes also called quantifiers or bounded repetition, that can be used to say that some string in the regular expression is repeated several times. For example, in this example, we say that A is repeated at least 5 times and at most 42 times, and B is repeated exactly 100 times. We obtained a large dataset of regexes from GitHub, network intrusion detection systems, SNORT and Bro, and from the industry. And after removing regexes with unsupported features like lookarounds, back references, we were left with something like 450k regexes. Then we try to see how much do the numbers occurring in the counting expressions in the regex, like here, affect the size of the DFA that is constructed for the regex. Then we want to see how many times is the DFA bigger than 1000 states. We use the threshold of 1000 states because often the size of the cache for the DFA is something around 1000. We classify the regexes into three sets. Regexes with no counting, where the probability of having a large DFA is very low, with counting bounds less than 20, where the probability is a little bit higher, but still very low, and with the sum of counting bounds over 20, where the probability of having a large DFA is quite high, around 20%. We use this information about the vulnerability of regexes with counting to create a ReDoS generator. The generator works by creating an input text by searching through the deterministic finite automaton for the regular expression, trying to generate a non-matching text. We try to get non-matching text in order not to allow the matcher to accept before reading the whole text, and also to be able to attack backtracking matchers. When doing this search for the DFA, we try to prefer macro states that are unvisited in order to have low cache utilization of the matcher, and that are big in order for the state to have it hard to generate the successor state. For example, here, if we try to get the successor of the state Q and T, we have three options, and we can take the last one because it has the biggest macro state. By doing this, we try to enforce the nonlinear runtime of the matcher. The issue here is how can we navigate to the big macro states? Because a priori, we don't know where are the big macro states and how to get to them, because the DFA is too big to be constructed. It can have, for example, billions of states. We address this by using a different formal model than a DFA. We use the so-called counting set automaton, which we introduced previously in our UPSLA paper, which is a formal model that can be used for compact representation of regular expressions with counting. The generator is implemented in a tool called Gežitka. We performed experiments to see how good we are in generating ReDOSes for non-backtracking matchers. For this, we took the same data set of regexes as in the previous experiment and kept only those regexes with the sum of counter bounds bigger than 20, which gave us 8,099 regexes. We also compare with other ReDoS generators. However, know that all of these generators target backtracking matchers. As far as we know, we are the first ones to target non-backtracking matchers. For each of the generator and each regex, we generated 50 megabyte input text and tried it on different matchers. In the first experiment, we tried to see how many ReDOSes we can generate for standard matchers. Here, the criterion for what is a ReDoS was that the time of matching of the matcher needs to be more than 100 times longer than average for the given matcher on random input. Results for other ReDoS criteria are in the paper. Our tool Gežitka uses 4 different strategies for exploring the counting set automaton. Counting, which is using the counting structure in the regular expressions, one line, which is targeting specifically Hyperscan, and 2 more algorithms I will not go into. You can see that counting is giving best results on these 4 leftmost non-backtracking matchers. For Hyperscan, one line performs better. And the last column here is CA, which is our matcher based on counting set automata, the same formal model that is used for generating the ReDOSes. In the right-hand side of the table, you can also see performance of our algorithm on backtracking matches in the common programming languages. Although we do not target them specifically, we give better results than the other ReDoS generators that focus on backtracking matches. We also try to see whether we can use our generator to attack real-life security solutions. For this, we use a different data set of regexes. We use real-life rule sets for SNORT. From this, we filtered out unsupported regexes and regexes where the sum of the repetition bounds was less than 20. By doing this, we obtained something around 1,100 regexes, and we were measuring the slowdown of evil text versus random text. We first tried to play with SNORT running Hyperscan as the regular expression matching engine. Here we perform two experiments, one for the MTU of 1.5 kilobytes and another one for the MTU of 9 kilobytes, which corresponds to Ethernet jumbo frames. In the left-hand side for the 1.5 kilobytes, you can see that we can, in many cases, obtain a slowdown of 10, 20, or even 40. And in some cases, we can even get to the slowdown of 100. In the right-hand graph, which is for the jumbo frames, you can see that everything is shifted more to the right. And in 32 cases, we can get a slowdown of at least 100, which is quite a lot. It is interesting to notice that you don't even need to have big counting bounds in the regexes. For example, here we could have 35 and obtain the slowdown of 214 for the jumbo frames. The other real-world security solution that we tried was the NVIDIA BlueField-2 data processing unit. This is a card that contains hardware-accelerated regex matching unit with a throughput of around 40 gigabits per second. Here we tried 617 regexes because from the original 1100, some of the regexes contain some features not supported by the regular expression matching unit on the card. The results can be seen here, where you can see that in 125 cases, we achieved a slowdown of 10 to 100, and in something around 100 cases, the slowdown was even bigger. For example, in 16 cases, the slowdown was even over 500 times. The winner here was this regular expression, where the obtained slowdown was around 2200. This brings me to the conclusion of the talk. Our main point is that non-backtracking regular expression matches are not a silver bullet against ReDoS. They can still be attacked, for example, by attacking counting in the regular expressions. We created a generator that does this, Gadgetka, and can be used for generating these ReDoSes. The mitigations are the obvious, for example, by putting limits on the time, input size, or by disallowing counting in the regular expressions. Another thing you can do is to over-approximate the counting into a star. You can also use Gadgetka to detect the vulnerable regexes. And the last thing, you can use a better regex matching technology, for example, based on the formalism of counting set automata. Thank you for your attention.